Hello lovelies, in this video we're going to be going through Cambridge International A-Level Chemistry, paper 4 that we've written for 2024. So what we want you to pay attention to in this is how we can work through things quickly, what sort of tricks and tips we can use to make sure we are actually hitting things at 1 mark per minute.
Sulfur trioxide, SO3, is manufactured from sulfur dioxide and oxygen by the contact process. The standard entropies are shown in the table below. Here we're asked to calculate the standard entropy change for this reaction. So we need to remember that the standard entropy change is equal to the sum of the entropy of the products minus the sum of the entropy of the reactants. So what we need to do here is have a look at our balanced equation and work out what the sum of the entropy changes of the products will be. Here I can see that there's two SO3s. So I'm going to do 2 times 256.2. So now we're going to subtract the sum of the entropies of the reactants, and we have SO2 and oxygen here. Don't forget that there's 2 SO2s. So I'm going to subtract 2 times 248.5. And then I also need to subtract the 205, and there's just 1 oxygen there. Notice how I've been very careful with brackets here. You could just subtract and subtract again, and that would be absolutely fine as well. So long as you get the same answer as me, you're golden. But if there is a mistake that pops up, I would argue maybe it's something to do with negatives and things. So simplifying this, I end up having that entropy change equals 512.4 minus 702. So if I just pop this into the calculator now, I find that delta S is equal to minus 189.6. And that is in joules per Kelvin per mole, as the table shows us. So now we're asked to calculate the free energy change, delta G, in kilojoules per mole for this reaction at 989 degrees C, and we're asked to show our working. So first off, let's remind ourselves of the equation. Delta G equals delta H minus T delta S. Now in this question we've been given delta H. If you look above next to the equation, we can see it's equal to minus 196.0 kilojoules per mole. We have also just worked out delta S. We said it was equal to minus 189.6 joules per Kelvin per mole. And the temperature, we're told, is 989 degrees C. Now, if we think we're going to put these straight into the equation, we would be wrong and we wouldn't get any marks. We need to be careful of units here. We need to convert delta S into kilojoules per Kelvin per mole to be consistent with the entropies and delta G. We do this simply by dividing by 1000. So that means that delta S is equal to minus 0.1896 kilojoules per Kelvin per mole. And also the temperature. This has to be in Kelvin, so we need to add 273, giving us a temperature that we can use of 1262 Kelvin. So now we have everything that we can use in this equation. I personally find when people keep getting these wrong, it's just because of the units. So that's a really easy thing for you to look out for if you keep getting these wrong. So we've got delta G equals minus 196 minus 1262 times by minus 0.1896. So here then, putting that into the calculator, we get that delta G is equal to 43.2752 kilojoules per mole. And there you have it, that is delta G. So now we're asked to explain whether this reaction is spontaneous at 989 degrees C. So that's the temperature that we were just looking at and that we've just calculated for. We should know that a spontaneous reaction occurs when delta G is less than 0, so when it's negative. So to work this out, we need to look at the value of delta G that we just got. Here we know it's equal to 43.2752. Now this is bigger than 0, it's not less than 0, and therefore this reaction is not spontaneous. Calculate the minimum temperature at which the reaction becomes feasible. So what this is at what temperature is that tipping point where delta G may start to become negative. And the easiest way to do this is just to equate delta G to 0 and solve it. So let's remind ourselves again of that formula. Delta G equals delta H minus T delta S. So if we replace delta G with 0, because that is the tipping point between positive and negative, and let's rearrange that to get T as the subject, I can see that I get T equals delta H over delta S. You can just remember that equation, okay? Now let's remind ourselves, we know that delta H equals minus 196 kilojoules per mole, and delta S we said was minus 0.1896 kilojoules per Kelvin per mole. Again, quick disclaimer, make sure that the units are consistent when using this. They both have to be using kilojoules in the units. So temperature then is equal to minus 196 over minus 0.1896. And that gives me a temperature of 1033.76 Kelvin. So that is the minimum temperature at which the reaction becomes feasible. A student found out that the above reaction does not occur spontaneously at very high temperatures. Explain the above observation. So here we need to have a think, okay? So we need to know that delta G has to be negative for it to occur spontaneously. So if we think about what we already know, okay, we know that delta H is negative, and we also know that delta S is negative. Well, as T gets very large then, what's going to happen is T delta S, due to the fact delta S is negative, is going to become very negative, okay? So the bigger T is, the more negative T delta S becomes. And due to the fact that there's this negative in front of it, this negative is going to become positive. So although delta H is negative itself, the more negative T delta S get means that we're adding, due to that minus, a bigger number. And that means eventually, as T gets bigger and bigger, delta G will end up eventually becoming positive. So it's just that battle between the fact that T delta S is a negative value and this negative in front of it, meaning that you're adding T delta S essentially to delta H. Now eventually that means that the balance will go off and that T delta S will make delta G eventually positive, which means it is not spontaneous. This question is about the chemistry of the period 3 elements and the trends in their properties. Here we're asked to complete the table to give the formula and acid-base behaviour of some of the oxides of the period 3 elements. And this first part of the question really is like a memory-based question. So the formula of the oxide of sodium, so sodium oxide, this one we can work out. We know that sodium's in group 1 and oxygen is in group 6. So we've got Na plus, O2 minus, which will come together to form Na2O. However, the others we do just need to memorise. Silicon forms silicon dioxide, so SiO2, and phosphorus makes P4O10. So if you don't already know them, make a note of them and get memorising them. So next up, we need the acid-base behaviour of some of these oxides. Now this is another little bit of just fact recall. So to be honest, this table is perfect for you copying down and putting into your notes to learn. So really what we need to know here is that the general trend as we go across period 3 is it goes from basic to amphoteric to acidic. That is the trend as we move through. So starting us off, sodium oxide has basic behaviour. Aluminium oxide is the unusual one, that is amphoteric. And all of the rest, so silicon dioxide, P4O10, SO2, they are all acidic in their nature. So if you don't know that, then just copy out this table now and get learning it. Okay, so write an equation for the reaction that occurs when magnesium burns in oxygen. And we're asked to state the type of bonding in the oxide formed. Now this really is quite a simple equation. So we should know that Mg plus O2 will form MgO. And we know that's the formula because magnesium is Mg2+, oxygen is O2-, and therefore they can just come together, their charges are equal to form MgO. Now because of the O2, we can see that we need 2 Mg plus O2 makes 2 MgO. Now because we have those two ions, the magnesium, which is a metal, and the oxygen, which is a non-metal, we can see that the type of bonding that we have here is ionic. So in answer to the question, state the type of bonding in the oxide formed, the answer is ionic bonding. So the next part wants us to state the type of bonding in sulfur dioxide. So we need to know that sulfur dioxide is made up of sulfur, which is a non-metal, and oxygen, which is also a non-metal. So because of this, whenever we have two different non-metals bonding together, we have covalent bonding present. And so the answer to this one, the type of bonding in SO2, is covalent bonding. The oxides of sodium and phosphorus react with water. Here we're asked to write equations for the reaction of each oxide with water and give the approximate pH of the resulting solution. So for sodium, we said that the formula for sodium oxide was Na2O. So if we add water to that, we should know that these react together to form 2NaOH. So we could write that as 2Na plus 2OH minus. Of course, the benefit of writing that way is that real presence of those OH minus ions, which we know makes a solution alkaline. So we should know the pH of the solution we make here is around 14, dependent on the concentration. Okay, so next up, let's do this for phosphorus. So we have P4O10, and we said that that had acidic behaviour. So when this reacts with water, in this case we're going to add 6 H2O, and we end up making phosphoric acid. So we're going to make 4 H3PO4s. Now, this is something we need to learn, so if you don't know this, then get memorising it. We also need to know the pH, okay? So we need to know that this is going to have a pH of around about 1. Now, this particular topic, there is quite a lot of information that we need to get memorised. So if you're a bit shaky on this topic, use this as a real opportunity to think, oh, I don't quite know this topic as well as I should. Let's take a bit of time in memorising these different equations and the behaviours of these oxides. The elements in group 3 of the periodic table can form compounds and ions containing chlorine. An aluminium chloride molecule can form an AlCl4- ion when it reacts with a chloride ion. Name the type of bond formed during this reaction and explain how this bond forms in the AlCl4- ion. Well, we should all know that aluminium, as it's in group 3, has 3 electrons in its outer shell. Now chlorine has 7. What's going to happen here is these chlorines can bond to the aluminium by sharing an electron with the aluminium. However, there's this 4th chlorine ion. And because that's a Cl- ion, it's gained an extra electron. And what it can do is it can share a pair of electrons with the aluminium to then form a dative covalent bond. And that is how we get that 4th bond in AlCl4- as compared to just AlCl3. It's the fact that we have that chloride ion in there that's gained an extra electron, and therefore it can share a pair of its electrons with the aluminium, forming that dative covalent bond. So to make sure we get all of our marks here, first off we're just going to state that we have either a dative covalent or a coordinate bond, and for our second mark we're going to say that an electron pair on the Cl- is donated to the AlCl3. Finally here, we're asked to write the oxidation number of Al in AlCl4-. So overall, the whole charge of this ion is -1. There's 4 chlorines, each of which has a charge of -1. So we've got 4 times -1 there. So we need to go from 4- from the chlorines up to -1. And so to do that, we need to add 3. And so that means that the oxidation number of aluminium must be equal to +3. And so there's our answer to this one. Iodine reacts with propanone in the presence of an acid catalyst. So the reaction is shown here. The kinetics of this reaction was investigated by monitoring the volume of sodium thiosulfate used. Propanone was reacted with iodine in the presence of HCl. Then the samples were withdrawn every 5 minutes and the reaction quenched. The iodine remaining was titrated with a standard solution of sodium thiosulfate. Here we're asked to state and explain how you would quench the reaction. So the way that we're going to quench this reaction is by adding an excess of sodium hydrogen carbonate. And the importance of this is it's going to be able to neutralise and therefore remove with the acid catalyst, effectively stopping the reaction. The graph of I2 against time is a straight line, showing that the order of the reaction with respect to iodine is 0. There must be a large excess of propanone and hydrogen ions in this experiment to give this straight line. Explain the above statement. So we need to know that the importance of keeping those propanone and hydrogen ions so high is that it ensures that the concentrations of hydrogen ions and propanone remain virtually constant. Now that's important because if they stay constant, then any changes aren't going to happen, and therefore we're not going to see hydrogen ions and propanone affect the rate. Therefore, only the iodine concentration will be changing, and so we know that any changes in rate is purely due to that iodine concentration changing. Data obtained from the experiment is shown in the table below. Here we're asked to use the results to plot a suitable graph to determine the order of the reaction with respect to propanone and state its order. So we need to obviously put the axes on here, label the axes, put the units on. Here I'm going to put on my x-axis the concentration of propanone. I'm going to include the fact that it's times 10 to the minus 3, those concentrations, and include the unit of moles per decimetre cubed. I also have to do the initial rate. I'm going to put that on the y-axis. And although it doesn't have it in the heading on the table, I'm going to take out times 10 to the minus 5, because at the minute, it's just going to look really messy having that on the axis. Why would we do that when we can just simply take out times 10 to the minus 5? So now let's label these axes, okay? I can see that the concentration, the smallest it needs to be is 1.4 and the biggest is 8.4. So on this x-axis for concentration, I'm going to go up in 2s. Now looking at the rate, I can see that if we do take out that times 10 to the minus 5, we're going from 3.2 up to 19. So that means my scale needs to go up as far as 20-ish, okay? So I'm going to go up here in 5s, like you can see here. A really important thing is that all of your numbers, all of your points that you plot on, have to take up at least half of the space on this graph. You can't just like do a really small scale and group it up really small. You wouldn't get all of the marks in this question, and that's true of any sciencey graph questions. So now I'm going to plot the point. So the first point is 1.4 and then I go up to 3.2. Next one is 2.8 on the x-axis and then I need to go up to 6.4, so that's the next point. Then 5.6 against 13 and 8.4 and 19. Now let's do the line of best fit here. Now here I can clearly see that I have a straight line which is passing through the origin, and so I'm going to say that this is a first order reaction. And whenever you get this straight line through the origin with this constant gradient, we know that we have a first order reaction. State how you determine the order using the graph. Okay, so now we need to just put this into words. So we said it was first order, and our explanation is that it is a straight line with a constant gradient that goes through the origin. So just getting across this point that we have this constant gradient is going to get us our mark. So next up, when you double the concentration of H plus ions, the rate of reaction doubles. Give the rate equation for this reaction. Well, that's given us a bit of extra information here. We know that when we double the concentration of H+, the rate doubles. That means that the concentration and the rate are directly proportional when looking at H+ ions. Now that tells us that it's first order with respect to H+. And so that will always be the case if when we double the concentration we see the rate also double, or if we triple the concentration the rate also triples, or half it and it halves, that's when we have first order reaction. So here we've got rate equals K times the concentration of propanone, and we said that was first order from our graph, so that's to the power of 1, and then times by the concentration of H+ ions, again effectively to the power of 1. And of course, don't forget that when we have something to the power of 1 in any mathsy type question, we don't really need to write it, okay? So here we've got rate equals K times by concentration of propanone times by concentration of H+. And that is our rate equation. We don't include iodine in this rate equation because you might remember a couple of pages ago we saw that iodine was 0 order. So that means that we don't include it in any rate equations. So next up we're told that we have a 3-step mechanism that's been proposed for the reaction. We're asked to use the rate equation to predict which is the rate determining step. Well, what we need to remember is that the rate determining step has the reactants in the rate equation, okay? So that is how our rate equation is going to help us. If we go over and look at it, we can see that it has propanone and it has H+. Now, out of all of these steps, the one that has those two things in their reactants is going to be step 1. And therefore, step 1 is our rate determining step. So when you're ever asked about that, you want to use your rate equation, and the reactants that you find in your rate equation have to feature in your rate determining step. A student measured the standard EMF of a cell which uses the following half equations. Here we're asked to draw a label diagram to show how the student could have set up this cell to measure its standard cell potential. Okay, so here we're going to need 2 beakers containing a solution. We'll figure out what that solution is going to have in a moment. Now in each of those beakers is going to be an electrode, and those 2 electrodes are connected to each other via a voltmeter. Now dipping into each of these 2 solutions as well is going to be something called a salt bridge. So here we've got our little solutions, and we need to make sure that this salt bridge is submerged in each solution here, just like the electrodes are. So now we've got the key parts, let's label it. Let's label on our salt bridge, and then we've got our electrodes and our solution. So here we need to know what is in each of these, okay? So to work that out, you need to look at each of the half equations. So here, if we look at the fact, we've got Fe2 plus aqueous and Fe solid. Whenever we have a solid in the half equation, that is going to be our electrode. And any aqueous things are going to be found in our solution. So here we're going to have Fe2 plus in our solution, and because we're looking for the standard cell potential, we're going to have a concentration of 1 mole per decimeter cubed of each of these solutions. So that's that one half cell. Let's look to the other one now. And again, let's take a look at our half equation here. Here I can see that I've got copper 2 plus aqueous and copper solid. Now because we've got a solid in this half equation again, I'm going to put that as my electrode. So copper solid electrode and a copper 2 plus aqueous solution, again with that concentration of 1 mole per decimeter cubed. You might find sometimes that when you look at our half equations, there's only aqueous things, there's no solids at all. When that is the case, we still need our solid electrode though. So in those cases, we would use, for instance, a platinum electrode, something that conducts electricity still, but is relatively unreactive. Also, we could say, if that was the case, where there was more than one aqueous thing in our half equation, we would just put both of those in the solution. So say, for instance, if you had Fe2 plus and Fe3 plus, you would just write Fe2 plus slash Fe3 plus in your solution. However, that wasn't the case here, and as you can see, each of these electrodes are made up of parts of the half equation. So now we're asked to write the conventional representation of this cell. So we need to know that vertical lines represent changes in phase or state. A double vertical line represents your salt bridge. And we need to know that on the right hand side, we're going to put the parts that are in our most positive electrode, and the most negative electrode will be on the left hand side of this. We're also going to put the species with the highest oxidation state for each half cell next to the salt bridge. So here I've written down our conventional representation. I'm going to just go back over what I just said and explain how it's relevant here. So I mentioned that on the right hand side, I'm going to put the bits that have the most positive electrode potential. So that is what we have here. Therefore, on the left hand side, I have the most negative electrode potential, as you can see. Now, because when we look at the state symbols here, solid and then aqueous, we have this change in phase or state. That's why I've put this vertical line between the two of them. And the same goes over here for the aqueous and the solid copper. Now, the next thing to think about is the positioning of the Fe2+ and the copper 2+. Why didn't we write them in a different order, for instance, like the Fe2+ first, then the Fe, and then the copper first, and then the copper 2+. Now, our little rule that we use here is the fact that the species with the highest oxidation state for each half cell is the one that is written next to the salt bridge. So here we've got Fe2+ has a higher oxidation state than iron, and copper 2+ has a higher oxidation state than copper. So that's why we've written this in this way, and we're going to apply those same rules anytime you have to write conventional representation of a cell. So finally here, we're asked to give the overall equation for the reaction. So what I would do is I would look at my two half equations and I would flip the most negative of them. I would then have a little look to see if I need to balance the electrons. And a little glance, I can see I won't need to here. There's 2 electrons in each equation. And then finally, I'm just going to smush these together. So I'll cancel anything that pops up on both the left and the right hand sides. But then everything on the reactant side I will smush together, and everything on the product side I will smush together, okay? So looking at these sets of equations here, I can see that the one that is most negative is the iron half equation. So I'm going to flip that, and I'm going to write that as Fe goes to Fe2+ plus 2 electrons. Now I check out the electrons, and I can see here that they have the same number. So I can just cancel them out. I don't need to do any balancing. And then I'm going to smush them together. So I've drawn on my imaginary little dividing line here. And on the left hand side, I have Cu2+ plus Fe. And then over on the product side, I can see that I'm just left with Fe2+ and copper. So I'm going to write down here Fe2+ plus Cu. And that is our overall equation for the cell reaction. So now we're asked to calculate the standard electrode potential for this reaction. So let's remind ourselves of the half equations and the electrode potentials. Whenever I need to calculate the standard electrode potential, I use the fact that I can calculate it by doing the most positive electrode potential minus the most negative. So in this case, if I look at what options there are in my half equations, I can see that the most positive one comes from that copper half equation. So I've got 0.34. And then I'm going to subtract the most negative, which comes from the iron half equation, which is minus 0.44. Notice the double negative there, that's really important. So here I've got 0.34 minus minus or plus 0.44. And that gives me 0.78 volts. And that's my answer. Next up, we're asked to explain how the salt bridge provides an electrical connection between the 2 electrodes, okay? So we need to understand that that salt bridge enables ions to move through it. And that's what's going to complete this circuit. Obviously in the circuit we have a metal wire that connects the voltmeter to the electrodes, and that's going to have free electrons or delocalized electrons moving through it to conduct electricity. However, really importantly, to complete that circuit, the salt bridge allows the ions in the solutions to move freely. And so that is how the salt bridge provides an electrical connection between the two electrodes. Consider the following half equations and their standard electrode potentials. Here we're asked to identify an acid that will oxidise copper and explain your choice of acid. So let's go and have a look at the electrode potential for that copper half equation. So you can see it's 0.34. If we look at the electrode potentials of these two half equations here, we need to remember that the more positive electrode can act as an oxidising agent. And that's a really, really important fact here when it comes to looking for an acid that will be able to oxidise copper. Because we need to find an electrode potential that's relatively higher than that of the copper half equation to then oxidise the copper. And so it looks here like this first equation is the one that we need. And because we've got the NO3- ion here, we can say that nitric acid would be the acid that we use to oxidise the copper. And the reason being is that the electrode potential of the NO3- system is bigger than the electrode potential of the copper system. And so that's just what I'm going to write down here. We could write it in words or we could use this sort of equality sign, and that's what we need to understand. So if you weren't aware that the more positive electrode potentials can act as oxidising agents, and therefore that the most negative electrode potentials can act as reducing agents, then maybe stop for a minute and make a note of that fact so that you don't forget it next time. Consider the following flowchart starting with cyclohexane. Cyclohexane reacts with chlorine to form compound A. The reaction is initiated by the formation of chlorine radicals from chlorine. Here we're asked to state what is meant by the term radical. So this is a really important definition, so if you don't know it, make sure that you get learning it after this. So a radical is defined as a species with an unpaired electron. And so if you don't know that definition, get out your flashcards now and get writing it down. So next, after this, we're asked to state the conditions necessary to bring about the formation of chlorine-free radicals from Cl2. Now, this is another really important fact that we need to know for this topic. There's lots of little short, snappy marks that we can get through a little bit of knowledge here. The condition we need is ultraviolet light or UV light. And now another really key fact we need to know. We need to state the type of bond fission involved in the formation of chlorine radicals. We need to know that this is homolytic fission, and a lot of people get these very confused, okay? Let's remind you of what homolytic fission is. Remember that every covalent bond has a shared pair of electrons. In homolytic fission, each of those electrons in the shared pair go to each of the respective atoms in that bond. So in this case, I've done it for a chlorine molecule. You can see here that the electrons, one has gone to one of the chlorine atoms, and the other electron has gone to the other chlorine atom. That has formed two chlorine radicals, which, like we said, are species with an unpaired electron. Now, actually, free radical substitution, this topic here, is the only topic that we learn about at A-level that has homolytic fission in it. If they ask for the type of bond fission of any other type of reaction, the answer will be heterolytic. So now we're asked to write the IUPAC name of compound A. So let's remind ourselves of what that looks like, okay? Remember, it was a ring with 6 carbons with a chlorine coming off of one of those carbons. So because there's 6 carbons in a ring, it's cyclohexane, and due to that chlorine, it is chlorocyclohexane. And that there is our answer for our mark. So now we're asked to complete the table shown to show the mechanism of the reaction when C6H12 reacts with Cl2 to form compound A. Include all possible termination steps in your answer. So here we're asked to start with the initiation step. In this question, of course, we're told that we're reacting the C6H12 for Cl2, and so the initiation step is going to take place on the Cl2. So remember, in the presence of that UV light, we're going to have homolytic fission take place, and the Cl2 will form 2 chlorine radicals. Now that there is our initiation step. Next we have the propagation steps. And in propagation steps we always have one radical reacting with a non-radical to make one radical and one non-radical. Normally the radicals will sort of swap around with an atom on the other molecule. So here we know that we have C6H12 and we've just made some chlorine radicals. So we're going to take C6H12 plus the Cl radical, and what we're essentially going to do here is switch one of the hydrogens for that radical. So here we have C6H11 radical plus HCl. So now we've just made another radical, okay? So that radical we just made is what's going to go on and propagate into the next step. So here we're going to have C6H11 radical, and we're going to react it with Cl2 this time. Here again, our radical and one of the chlorines this time is going to play swapsy, and we end up with C6H11Cl plus Cl radical. So we've made that radical again at the end there. So propagation steps will always have two steps like that, so always look out for that. Finally, here we need the termination steps. And this question said it wants all of them. So you need to look at all of the radicals that were present in these reactions and start to team them up, okay? So you could have had two chlorine radicals come together to form Cl2, or you could have a chlorine radical with a C6H11 radical to make C6H11Cl. And the final option is going to be you take two of the C6H11 radicals, react them together to make a C12H22 molecule. All of those are all of the possibilities that we have here. So now we're asked to deduce the type of reaction that occurs in reaction 2 and reaction 3. So this is going back to what was on the previous page. Let's remind ourselves then of what happened in reaction 2 and reaction 3. In reaction 2, we had this chlorocyclohexane and it reacted to become an alcohol group, okay? So the Cl group became an alcohol group. We should know that this is a form of substitution, or we could write nucleophilic substitution, because we've literally just swapped up the chlorine for the OH. Now reaction 3, on the other hand, took that alcohol and it formed an alkene. Now we need to know that that type of reaction, when we go from an alcohol to an alkene, it's absolutely irrelevant that this is a cyclocompound. Any alcohol to an alkene is an example of an elimination reaction. So now we're asked to give the IUPAC name of compound C. So let's draw it out and remind ourselves of what compound C is. Here I can see it is a ring structure with 6 carbons and a CC double bond. So because of that double bond, I know it's an alkene, so it will end in -ene. Because it has 6 carbons, it's hexene, and because it's in a ring, it is cyclohexene, so that is its name. So for the last part of this question, we're asked to draw the structures of the product formed when compound C, that alkene, reacts with cold dilute acidified potassium manganate. So to answer this, we need to know that when we have an alkene and it reacts in the presence of a cold dilute acidified potassium dichromate, we form a diol. So what's going to happen essentially is that CC double bond is going to be cut open and we're going to attach 2 OH groups to either side of that CC double bond. So here is what we get. So that's what you'd need to draw to get your marks. Now we need to think about what's going to happen if we react this alkene with hot concentrated acidified potassium manganate. So the important facts that we need to know here is that this hot concentrated acidified potassium manganate is going to oxidise this substance. It's going to end up breaking down that C to C double bond and it's going to form a C double bond O, a carbonyl group. And it's going to form 2 carbonyl groups, okay, either side again of that breakage. That's then going to get oxidised to form a carboxylic acid. So what we need to imagine here is we're going to break open that double bond, meaning that we've essentially cut this ring open and now it's just a straight chain molecule. It's going to have 6 carbons on it, and on either end of those carbons that were the CC double bond, we're going to have a carboxylic acid. Because due to the structure of this, we would have formed 2 aldehydes because they would have been on the ends of this chain, and then we further oxidise these to form, of course, our carboxylic acids. So this here is the structure of what we make when we react the alkene that we have here, the cyclohexene, with hot concentrated acidified potassium manganate. This question explores some reactions and some uses of cobalt compounds. Here we're asked to complete the electronic configuration for a cobalt 2+ ion and a cobalt 3+ ion. Now first things first, I'm going to have a look at the periodic table and remind myself of how many electrons there are in cobalt. I can see that there are 27 electrons in an atom of cobalt, okay? An atom. Before we work it out for the ions, I'm just going to take a moment to write down the electronic configuration of cobalt. So cobalt will have a 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and then 3d7 configuration. Notice if we add up all of those numbers, all of those powers, then we get that number of 27. However, here, we're being asked about the cobalt 2+ ion. We should recognise that we're going to lose electrons from the 4s subshell before the 3d subshell. So that means when we need the electronic configuration for cobalt 2+, where we need to lose 2 electrons, we're just going to lose that s subshell. So the electronic configuration of cobalt 2+, as you can see here, is 1s2, 2s2, 2p6, 3s2, 3p6, and 4d7. And that ends up giving us the 25 electrons that we would find in the cobalt 2+ ion. So next we're asked about the cobalt 3+ ion, okay? So here we've lost 3 electrons from that outer shell. So we're going to first lose them from the 4s subshell, that's still correct, but the third electron we're going to lose from the 3d subshell. So that gives us 1s2, 2s2, 2p6, 3s2, 3p6, and now we've got 3d6 because we lost an electron from the d subshell. So now we're asked to draw a diagram to illustrate the structure of the shape and the charge on the complex ion formed in each of the following reactions. And we're asked to name the shape of the complex formed. First up, we've got cobalt 2+ in an excess of Cl-. So we should know that due to the size of the chloride ligand, it's quite large, we can only actually fit 4 chloride ligands around the cobalt ion. Now that ends up leaving us with a tetrahedral shape. Another thing we need to consider is the charge. 4 Cl- ligands, together with the 2+ cobalt, gives us a 2- charge, because 2 plus 4 times -1 gives us 2-. Now here the shape that we have is going to be tetrahedral, so we need to write that down. Okay, so now we're looking at cobalt 2+ with an excess of ammonia. Now when we have an excess of ammonia present, what we have is a ligand substitution reaction taking place. And because that cobalt was aqueous, it would have had water ligands. However, here when we add this excess of ammonia, we replace those water ligands with ammonia ligands. Due to the size of ammonia, we can fit as many as 6 different ligands around the cobalt ion. So what we end up having is this octahedral shape. We need to make sure we know how to draw that octahedral shape. We need to recognise that the ammonia ligand is neutral in charge, it doesn't have a charge, and so the only charge of the complex ion is going to be coming from that CO2+ ion. So there you have it, that is what an octahedral shape complex ion looks like. You can see I've made the effort here to make sure that all of the coordinate bonds are touching the nitrogen of the ammonia. Now the reason for that is because ammonia obviously has a nitrogen, and it's that nitrogen that has the lone pair of electrons that can form these coordinate bonds with the cobalt. So there we have it. If you're not familiar with those shapes and that type of bonding, make sure you get learning them. So here we need to state the type of reaction taking place when cobalt 2+ reacts with an excess of ammonia. And I mentioned this before. What happens here is we get a ligand substitution reaction happening, or we might call it ligand exchange. And this is where what would have been the water ligands in the aqueous cobalt 2+ get replaced with NH3 ligands. So now we're told that cobalt can form these 2 different compounds. These 2 compounds are structural isomers of each other. Here we're asked to state the oxidation number of the cobalt in both of them. So let's get started with the first one here. I'm writing this out a bit bigger so that we can look at it in a bit more detail. See how we've got the square brackets next to chlorine? That tells us that those are going to be ionically bonded to each other. So because chloride ions are negative, that means that the complex ion must have a positive, a +1 charge, because that's going to be attracted to the Cl- to form this bond. So we know that the complex ion needs to have a charge of +1 overall. We also know that ammonia has a 0 charge, and NO2 we should be familiar with the fact that that has a -1 charge, and here we have 2 of them. So here we've got cobalt plus 0 charge from the ammonia, plus the -2 that comes from the fact that we have 2 of these -1 charged NO2s. And overall we said that that has to have a charge of +1. So we can rearrange this now to work out what charge cobalt must have for the charge of this overall complex ion to be equal to +1. So here if I take that +1 and I add 2, I get the oxidation state of that cobalt, and it's going to be +3. So now let's do exactly the same for part 2 here. This has a slightly different structure. Like we said, it's an isomer. In this case, we've got the square brackets of the complex ion next to an NO2. So that means we're going to have this ionic bond between the complex ion and the NO2- ion. Now, because that has a charge of -1, that NO2- ion, that means that again our complex ion has to end up having a charge equal to +1. Now again, we know that ammonia has a charge of 0, NO2 has a charge of -1, and the chloride ion has a charge of -1 as well. So looking through this again, we can say that the charge on the cobalt, +0 from the ammonia, -1 from the NO2, and -1 from the chlorine, has the total +1, that charge of the complex ion. Doing the exact same maths and rearranging this, I can see that the cobalt is going to have the oxidation number of +3. And so that is the answer. It's actually exactly the same as its isomer in part 1. And so there we have it. Those are the oxidation numbers of those cobalts. Now we're asked to draw the geometric isomers of this complex ion. So having a look at this here, I can see that it has 4 ammonia ligands and 2 NO2- ligands. That means it's got 6 coordinate bonds, which tells me straight away it's going to have this octahedral shape. Now, because there's 2 NO2- ions, I can use this to structure my cis and my trans isomers. If I put those NO2 ligands on opposite ends of my complex ion, then that's going to represent a trans isomer. The ammonias will go on all of the other coordinate bonds. However, wherever we can put the NO2s on polar opposites, can be top and bottom, or it could be top right and bottom left and so on, that will be our trans isomer. Now, once we've worked out our trans isomer, everything which isn't trans is going to be cis. So here we've still got 2 of the NO2- ligands and 4 NH3s. And so long as we don't put the NO2s on opposite coordinate bonds, we have a potential cis isomer. So here I've given one example. I've got them right next to each other. However, they could have been in different orientations as well. Like I said, so long as they're not polar opposite, it will work as a cis isomer. So I'm just going to highlight some examples of where you could have instead put the other NO2 to have got other potential cis isomers. So you could have put one here, and you could have put one here. They're not polar opposite, so that would work as a potential cis isomer. Another option would be maybe if you put an NO2 here and an NO2 here, that would also work as well. Again, they're not polar opposites. So actually there's really quite a lot of different permutations that you can have of the cis isomer. And likewise with the trans, so long as they're opposite each other, then that could provide a potential trans isomer. So I hope that that's clear and you're familiar on how we can draw some of these geometric isomers of complex ions. A simple test tube reaction can be used to distinguish between these 2 different compounds. Identify a suitable reagent for the test and state what you would observe. So this is quite a tricky one really, but there is a test we can do. Remember we said how in each of these the complex ion was going to be ionically bonded to, in the first case, the chloride ion, and in the second case, the NO2- ion. That means that in this first compound here, we have chloride ions in solution. And so, because of that dissociation when we put an ionic compound in water, we can test for those chloride ions. Remember that the classic test for chloride ions is if we add silver nitrate to that solution, a white precipitate of silver chloride will form. And that observation of a white precipitate for this first compound and not the second will be a way that we can distinguish between them. Valence shell electron pair repulsion theory is a model of electron pair repulsion that can be used to deduce the shape and bond angle in a simple molecule. Here we're asked to draw a Lewis structure for each molecule or ion and name the molecular geometry of each. So here we're going to have to do little dot and cross diagrams, Lewis structures of each of these ions or molecules. Let's start with BrF3. Now we know that Br has 7 electrons in its outer shell, and fluorine also has 7 electrons in its outer shell. Now due to this, what we're going to see is around the bromine, we're going to have 3 bonded pairs of electrons. However, we're also going to have 2 lone pairs of electrons. And that is, of course, going to affect its molecular geometry. So when it comes to now drawing the Lewis structure, we're going to draw it just like this, okay? So we're going to show those bonds with the fluorine, and then we're going to show these regions of lone pairs of electrons in little balloons here. So we need to know that when we have a shape like this, we name it T-shaped. And so that is what we need to say and what we need to draw to get our mark for that molecule. So now let's have a look at POCl3. So looking at this particular one, I know that phosphorus is in group 5, so it has 5 electrons in its outer shell. I know oxygen has 6, so it can gain a full outer shell by sharing 2 electrons with the phosphorus, and the chlorine can share 1 with the phosphorus to again get a full outer shell. So when drawing the shape of the molecule here, we can see that we have 4 regions, bonded pairs of electrons, one of which is a double bond between the phosphorus and the oxygen. So because of that 4 bonded pairs and no lone pairs, we have a tetrahedral shape. So when we draw the shape of this molecule, it is going to look just like this, making sure that we show that 3D nature of the molecule. And here, as I mentioned just then, the name of the shape is tetrahedral. And we recognise that because of those 4 bonded pairs and no lone pairs. So now we have an ion, we have ClF4-. So chlorine and fluorine all have 7 electrons in their outer shell. And the negative ion here means that we have gained an additional electron. So here, all of those fluorines, of course, have 7 electrons. And it can share an electron with the chlorine to get a full outer shell. Now the F- of this is an ion that has gained an electron from an external source. So we're going to have the 7 electrons from the fluorine and it has gained an additional electron. Now that then completes a dative covalent bond between the fluorine and the chlorine, and by putting in the rest of chlorine's electrons, I can show the formation of the bonds between the other chlorines and fluorines. So it shares 1 electron with the others. So here you can see I've only got 3 electrons so far, and chlorine has 7. So I need an additional 4 electrons, which means I'm going to have 2 lone pairs of electrons. Now here in this structure, because I have 4 bonded pairs of electrons, and I also have 2 lone pairs, that's going to affect the shape here. So when I draw the shape of ClF4-, I actually end up getting a square planar shape. And the reason for this is when I have those lone pairs of electrons which go above and below that chlorine, they are going to repel away so that we end up with this square planar shape. And so that is that table now finished. So now we need to state the FCl-F bond angle in Cl-F4-, and we should know that whenever we have a square planar shape, we have a 90-degree bond angle. Peroxynitrous acid is formed as an intermediate during the oxidation of acidified aqueous solutions of nitrites to nitrates using hydrogen peroxide. Consider the following hydroxynitrite to answer the following question. Complete the following dot and cross diagram of the bonding in peroxynitrite. For each of the 4 atoms, show all the electrons in its outer shell. So here we know it's a negative ion. I know that oxygen has 6 electrons in its outer shell and it needs to gain 2 more. Now it can do that by sharing with nitrogen. And you can see in this region here I've got a double bond now. Oxygen's put 2 of its own electrons in and nitrogen's shed 2 of its own, and we now have a full shell for the oxygen. So now let's look at the nitrogen. I know that nitrogen has 5 valence electrons. So here we've got 1, 2, 3, 4, 5 electrons for the nitrogen, and it needs to gain 3 to get the full outer shell. Now it already had 2 that it gained from the oxygen on the left hand side, and the diagram's already completed that it's got 1 from the oxygen in the middle there. So that nitrogen is now looking good and it has a full outer shell. Now let's look at the next oxygen. But oxygen has 6 electrons in its outer shell. So this oxygen in the middle here, you can see can get its full outer shell by, obviously, it has shared an electron with the nitrogen. And if it shares an electron also with the other oxygen, then it has gained the extra 2 electrons that it needed to get its full outer shell. So now, as you can see, this oxygen here has 8 electrons in total. Finally, we're on to this last oxygen. Like we said, oxygen has 6 electrons in its outer shell. That means in this case, it would be short of 1 electron. However, don't forget that this is a negative ion, which means that part of it has gained an electron. So here I have shown that on my diagram by filling in an extra electron in the little square as the key indicated. And you can see that now that oxygen also has a full outer shell. So we have completed our dot and cross diagram. Here we're asked to state the hybridization of the following atoms in peroxynitrite, considering the Lewis structure of the peroxynitrite ion. So here we've got the nitrogen atom, we need to work it out, and we'll look at that one first. So I've got a little trick that can help us work out the hybridization. So the first thing we want to do is to count the number of atoms connected to this atom we're talking about. Secondly, we want to count the number of lone pairs of electrons. Finally, we simply want to add those 2 things together. And once we've done that, we've got this little trick that we can learn, okay? So if that number is 4, that tells us that we have sp3 hybridization. If we get 3, then that's sp2 hybridization. And if we get 2, then it's sp hybridization. So let's put this into practice then for the nitrogen. I can see that this nitrogen is connected to 2 other atoms, 2 different oxygens. So I'm going to get 2 first. I can see here that I have 1 lone pair of electrons, don't I? I just have this one here at the top. And so I'm going to do 2 plus 1, which gives me 3. And I know that that means it's going to be an sp2 hybridization. So there we have it. Next, let's do it for the oxygen attached to both the nitrogen and the oxygen. Let's use the same method. How many atoms is it connected to? 2. How many lone pairs does it have? 2. That gives us 4, and that means that we have an sp3 hybridization. And so that is our answer. So that wasn't so bad, was it? Acid-base titrations involve a neutralization reaction between the analyte, the solution with the unknown concentration, and the acidic basic titrant. 30 centimetre cubed of 0.5 moles per decimetre cubed sodium hydroxide solution was added gradually in 1 centimetre cubed portions to 20 centimetre cubed of 0.5 moles per decimetre cubed of weak acid. Here we're asked to give the Ka expression for HX. And first things first, I'm just showing the dissociation of HX into its ions H plus X minus. I know that the Ka equation is essentially products over reactants. So here in this case, because we're talking about the acid HX, Ka is going to be equal to the concentration of H plus times by the concentration of X minus divided by the concentration of HX. And it's always going to follow that pattern, tweaking it ever so slightly dependent on your specific acid. Now we're asked to calculate the initial pH of the acid HX. Now if we look at the information that we've been given, you can see that we know that the concentration of the weak acid HX is 0.5 moles per decimeter cubed. Okay, so that information will be helpful. However, here we can make a really useful approximation, because in this solution, when we just have HX and we haven't added any hydroxide yet, we can say that the concentration of H plus is approximately that of the concentration of X minus. This means we can simplify the equation of Ka to the concentration of H plus squared over the concentration of HX. So we've lost a whole variable that we would have otherwise needed. If we rearrange this now to find out what the concentration of H plus is, we can see it's equal to the square root of Ka times by the concentration of HX. So if we substitute the numbers in here, we know that Ka is equal to 1.7 times 10 to the minus 5, and we times it by the concentration of HX, which we said was 0.5. If we pop that into a calculator now, we find the concentration of H plus. So that ends up giving me that a concentration of H plus equals 2.958 times 10 to the minus 3. And the reason why we need that is because our pH equation states that pH equals minus log H plus. So if we do minus log of 2.958 times 10 to the minus 3, I find that I get a pH equal to 2.5. And that's my answer. So next up, we need to calculate the volume of sodium hydroxide required to neutralise the HX acid. Now if we look at this particular question here, notice we have the same concentrations of sodium hydroxide, and therefore we will just need the same volume of sodium hydroxide as we have of weak acid to neutralise it. So in this question, we don't actually need to do any calculations, although you can. We just need to appreciate that if we have the same volume and the same concentration, we will have the same number of moles. And that's how we neutralise something fully. So the volume is 20 centimetres cubed. So now we're asked to calculate the pH of the solution after all of the sodium hydroxide is added. So remember we said that 20 centimetre cubed of that NaOH added neutralises the acid. So there's no H plus, no OH minus ions present at that point. However, if we keep adding more until we've added eventually 30 centimetres cubed, then that means that to that now neutral solution, you've added an additional 10 centimetre cubed on top of that initial 20 centimetre cubed that of course neutralised. So let's work out the number of moles of sodium hydroxide that were present in that additional 10 centimetre cubed. So that's 0.5 for the concentration, times 10 for that extra volume over 1,000, which gives me the number of moles of NaOH equal to 0.005. And because of course the sodium hydroxide only has one OH in it, that's also the moles of hydroxide ions. Now we need the concentration of hydroxide ions. Now remember that the volume of this solution isn't simply 10 centimetre cubed anymore. No, it's the 20 centimetre cubed of acid you had, plus all of that 30 centimetre cubed of hydroxide that you added on top. So in order to get the concentration, you are going to need to take those moles of hydroxide ions and divide it by the total volume and times it by 1,000. So here I get 0.005 divided by 50 and then times by 1,000 gives me a concentration of the hydroxide ions equal to 0.1 moles per decimetre cubed. So once we know that concentration of OH minus, there's a few different ways that we could work out the pH of this solution. I'm going to show you one way, you could try some others dependent on how you've learnt it. Now we can start here by working out what the POH is. Now to get that, we do minus log of the concentration of OH minus ions. Popping this into the calculator, I get a POH of 1. Now the reason why this is a method that we can use is that the pH is going to be equal to 14 minus that POH. POH is just the measurement from the other direction essentially, so rather than starting from 0 going up to 14, you start from 14 and go down to 0. So here if I do 14 minus that 1, I get 13. So here the pH of this solution is 13, which kind of makes sense, doesn't it, considering you have this alkaline solution from adding the sodium hydroxide. So that's all we need to do to get our pH. But there are other methods that maybe you'd use. It depends on how you've learnt it and what you're most comfortable with. So long as you get 13 at the end, then you've done a good job. So now we're asked to sketch a graph to show how the pH changes during the titration. So first things first, let's remind ourselves of what we added to what in this scenario. So we should know that we added sodium hydroxide slowly to a weak acid HX. So that means that we started with this weak acid and you gradually added this strong base. Now that's going to help us get the correct shape of our titration curve. So let's now draw on our axes, okay? So along the x-axis, I'm going to write the volume of sodium hydroxide added. On the y-axis, on the other hand, I'm going to have the pH. And I'm going to do the axes, I'm going to label them starting down at 0 and going all the way up to 14. So now that we've got this, we need to have a think about the shape of the curve. Now titration curves always have this general S shape with a vertical region when neutralisation occurred. So let's remind ourselves of when that did occur. We found out in an earlier part of the question that this solution neutralised when we added 20 centimetre cubed of sodium hydroxide. So for that reason, we know that that's where our vertical region of our titration curve will be. We also know we started with a weak acid. Now because we have a weak acid, we're going to start our curve at a pH of between, say, 2 and 3. Then we're going to go along, we're going to have a vertical region at 20 centimetre cubed, like we said, because that's what we needed to neutralise. And we're going to end, because we have this strong base, somewhere between 12 and 13.7. Very high up anyway. So those are our key features that we need in this curve. Of course, we need this S-shaped curve. We're going to have this gradual rise starting from a pH of about 2.3 and then having this vertical region where the pH suddenly jumps up at 20 centimetre cubed and then flattening off and ending with a pH somewhere between 12 and 13.7. So those are the general things to look out for. Just make sure you always know what you started with. If we started with a strong base, for instance here, this curve would start high and then it would drop down suddenly and end low. We just need to be very careful of what we're starting with and what we're ending with in the titration. Redox titrations involve an oxidation and reduction reaction between the analyte and the titrant. A solution of H2O2 was analysed using a redox titration with KMnO4 under acidic conditions. Deduce the half equations for the above redox reaction. Now, I would recommend that you get your data sheet out here. It has lots and lots of half equations in it in the standard electrode potential and redox potentials part of it. So here I know I've got potassium manganate, so I can scroll through this list and I can see a half equation that involves manganate ions. I'm going to write that down. So I've got MnO4 minus plus 8H plus 5 electrons goes to Mn2 plus 4H2O. So I have just used my data sheet here to get that. Then I know that a solution of hydrogen peroxide was analysed using a redox titration. So if I have a look through this list, then I can find an equation which is the other way around, which states that O2 plus 2H plus 2 electrons makes hydrogen peroxide. Now because here this is saying that we have a solution of hydrogen peroxide, I know that I can then actually reverse that. And also, of course, if we look at the electrode potentials here, we know that we flip the most negative electrode potential. Well, that is the one for this hydrogen peroxide half equation. So it makes perfect sense that that is the one that we're going to flip because it has that most negative electrode potential. So when it comes here to deducing those half equations, I'm going to keep the manganate one as is, but I'm flipping the one that I just said. I'm going to write it now as H2O2 goes to O2 plus 2H plus 2 electrons. And those there are my two half equations that I need for the mark in this question. So the next part of this question wants us to deduce the overall equation. So to do this, I like to imagine my two half equations And I like to imagine an imaginary line separating the reactants and the products here. Now, the first thing I'm going to want to do is balance the electrons. I can see the first equation has 5, the second one has 2. We need them to have the same number of electrons. So if we multiply that first equation by 2 and the second one by 5, we will do that and we will fix it. So let's write down those two new equations then. So we're going to have 2MnO4 minus plus 16H plus 10 electrons makes 2Mn2 plus 8H2O. I've just multiplied all of those by 2. And then this second equation, I'm going to multiply everything through by 5. So I've got 5H2O2 goes to 5O2 plus 10H plus 10 electrons. And there we have our two half equations all balanced. We've got one last step to get this overall equation. I'm going to separate the reactants from the products, cancel anything I can, so all the electrons will cancel, and I can cancel out 10H plus from both the left and the right, just leaving me with 6 H pluses on the left. And I'm just going to smush them together now. So by doing that, I'm just going to take all of the reactants that remain on the left-hand side and write those together as my reactants. And then I'll take all of the products on the right-hand side and just write them together as my products. So here I have 2MnO4 minus plus 6H plus 5H2O2 is going to make 2Mn2 plus 8H2O plus 5O2. And that there is my overall equation, and that will always work in these cases. Balance the electrons, see if you can cancel anything, and then smush them together. So there we have it, that's our answer to part 2. Next up, we're told that 25 centimetre cubed of hydrogen peroxide was titrated with 0.2 moles per decimetre cubed of potassium manganate under acidic conditions. The volume of potassium manganate required to reach the endpoint was 17.50 centimetres cubed. Here we need to calculate the volume of gas measured at room temperature and pressure that could be produced during this titration. Now, looking at our overall equation, I can see that only one of these products is a gas, and that's the oxygen. Now, we've got enough information here to work out the moles of manganate ions, and therefore we can use the ratio, the 2:5 ratio between manganate and oxygen, to work out the moles of oxygen, and then from there the volume of gas we're asked to find. So the first thing I'm going to do here is work out how many moles we have of potassium manganate. And the moles of potassium manganate will just be the same as the manganate ions in this equation due to the fact that there's only one manganate in potassium manganate. So here this is going to be 0.2 times by 17.50, the concentration times volume, over 1,000, and that gives us a number of moles of manganate, 3.5 times 10 to the minus 3. Now, like we said, this is in a 2:5 ratio. So if we divide this number by 2 and then multiply through by 5, we will find the number of moles of oxygen that we have. Now that gives me 8.75 times 10 to the minus 3 moles of oxygen. So finally here, we weren't asked to find that, we were asked to find the volume of gas. Now, because this is an RTP, that tells us we can use the fact that 1 mole of gas occupies 24 decimetre cubed. Or, as they haven't specified a unit here, we could have said 24,000 centimetres cubed. So, as we know that we have 8.75 times 10 to the minus 3 moles of this gas, the volume is going to be equal to those moles times by 24 decimetre cubed. So the volume here is 8.75 times 10 to the minus 3 times by 24 decimetre cubed. And that ends up giving us an answer equal to 0.21 decimetre cubed. And that there is the answer that we needed here. That's the volume of gas that we had, because the only gas present in this reaction that forms is the oxygen. This question is about the use of spectrometry to gain information about the structure of organic molecules. X is an organic compound with a molecular formula C4H8O2. A student proposed the following structures for X. So we've got A, which is an ester, and here we have B, which has a carbonyl group, a ketone in this case, and an alcohol group attached. After analysis of compound X, the student obtained the following results. They got the following infrared spectrum of compound X, and they also got this carbon NMR spectrum. Here we're asked to give the IUPAC name of the compounds A and B. So, as I mentioned earlier, A, you can see it has an ester linkage, and there's a very specific way that we name esters. So, esters have the general form of something yl, something anoate. And those blanks come from the alcohol and the carboxylic acid that made that structure. So what we need to do is have a look at this ester. Let's imagine we're chopping it in half to separate it into its carboxylic acid and its alcohol. And I can see that the alcohol part is the bit without the double bond. So here there's 2 carbons, so it would be ethanol. And on the other hand, that would have been the part that originally was the carboxylic acid that may have made it. And so because there's 2 carbons here as well, this would come from ethanoic acid. So therefore the name would be ethyl, coming from the ethanol, and then ethanoate, coming from the ethanoic acid. So here we've got ethyl ethanoate. So now for B, we need to be careful here, because I can see 2 different functional groups. I can see that we have a ketone, and we also have an alcohol. So because of that, we need to include both parts of that in the name of our structure. Ketone will always be at the end of the word, which means that the alcohol bit can't end in -ol, it's going to end in -one for the ketone. Whenever that's the case, we can, instead of writing the alcohol as something -ol, we can write it as hydroxy. So here, because we have 4 carbons in our longest carbon chain, we've got butanone, and branching off of that on the 3rd carbon is the alcohol. So we're going to call this 3-hydroxybutanone. So now we need to deduce the correct structure for X by using the results obtained. So I've included here our infrared spectrum. So here on the infrared spectrum, I can clearly see that I have a strong peak at about 1700 centimetre -1. Now I know that that peak refers to a carbonyl group, a C double bond O. Now that tells me then that I do indeed have a carbonyl group. Now both of our options A and B had a carbonyl group. So now let's check out this other region. I can see that that tiny peak, we don't really include it. We're going to say that there's no broad absorption peak that would correspond to an alcohol. Okay, we would expect for an alcohol, or for an OH group at least, there to be a broad absorption peak between 2,500 and 3,300. Now because of that absence, we're going to say that there is no OH group. Now for that reason, we can really eliminate B. But let's have a look at the other information we're told too, just to back up what we're saying. So it's this peak here that's particularly important, this peak at about 170. Now because we have a peak within the region of 160 to 185, that's going to correspond to a carboxyl group. Now because we've just said from the infrared spectrum that there's no OH group, then that means that this must indeed be an ester. It can't be a C double bond OH, it must be a C double bond O, OR group, which would be an ester. So for that reason, because we can confirm this now, we can say that it is indeed what option A said it was. It is going to be this ester of ethyl ethanoate. And so that there is our answer. So in the next part, we're asked to sketch the proton NMR spectrum of compound X. So to do this, let's have a look at our structure that we said X is, which was structure A, and let's spot where all of the proton environments are. I can see here that I have 3 different environments. I have the first CH3 here, then I have these H's on this CH2, and then I have this final CH3 as well. So I have 3 different hydrogen environments here, and therefore I'm going to have 3 different peaks. Remember that the number of peaks tells us the number of proton environments. So what we need to do is go through these one at a time and analyse what we would expect to see in our spectrum so that we know what we need to draw on. So starting with our first hydrogen environment, the one that I labelled number 1 here, I can see here that this has 3 hydrogens within it. I can also see that it is next to a carbon that doesn't have any other hydrogens attached. It's attached to a C double bond O. Now if I look that up in the datasheet, I can see that I'm going to expect this to have a peak at between 2.2 and 3.0 ppm. Now because these H's are in an environment next to a carbon which neighbours a carbon that has no hydrogens attached, we can use the n+1 rule to add 1 to that 0 to say that we would expect peak 1 to be a singlet, just a single peak. So now let's look at the second environment. I can see that this is attached to an O, and because it is attached to an O, I can see that it's going to have a peak between 3.2 and 4.0 ppm. So because this is next door to 3 hydrogens, or carbon with 3 hydrogens, we're going to use that n+1 rule again to say 3 plus 1 is 4. We're going to expect to see a quartet, which is a splitting pattern of 4. Looking at this last peak now, I can see that this is just a CH3. So if I look in the datasheet, I can see that I'm going to expect a peak for this between 0.9 and 1.7 ppm. And in this case, I can see that the hydrogens are attached to a carbon, which is next door to a carbon that has 2 hydrogens attached. So again, using the n+1 rule, 2 plus 1 gives us 3. So we would expect this peak to be a triplet, to have a splitting pattern of 3. So now I'm going to do a very rough little diagram here, okay? I'm going to show that at about 1 ppm, I'm going to have a triplet, which corresponds to that RCH3. At about 2.5-ish, I'm going to expect a singlet, due to that CH3C double bond O. And at about 3.5-ish, I'm going to expect a quartet, which corresponds to that CH2OCO. So that's what we would expect to see here. We're going to get 1 mark for each of these peaks. Identify the reagents and the conditions needed to produce compound X in a lab. So we've talked a bit about this before. Compound X, which was compound A, is an ester. And we talked about before, when we thought about how we name it, about how we would have made it in the first place. So we said that an ester is generally made by taking an alcohol and reacting it with a carboxylic acid. And we said in this case that the carboxylic acid and the alcohols that this came from would have been ethanol, coming from this region here with 2 carbons attached, and ethanoic acid for the carboxylic acid, because on the other side here again we've got 2 carbons, but that would have been coming from the carboxylic acid part. So we know what reagents we need then to make this specific ester. We're going to specifically state we need ethanol and we need ethanoic acid to react together. So then we need to think, well, what conditions do we need? So in order to react these together to make an ester and water, we need to have reflux and concentrated sulfuric acid. So those are our conditions that we need to make a note of to get our full marks here. So if you weren't aware that those are the conditions that we need to make an ester, make sure you make a note of them. So now we need to draw the structural formula of 2 isomers with the molecular formula C4H8O2 that are esters. So we need to come up with something different to what we've already got here. So let's have a go at moving that ester linkage elsewhere in this structure. Let's instead imagine it was made of maybe methanoic acid and propanol. That would work. So here, one potential option that we could have is this one here. So you can see that this would have been made from our methanoic acid and propanol. So here we've got propyl methanoate. So another option that we could have is we could maybe introduce a little bit of branching perhaps. Imagine we keep the first section the same, so coming from some methanoic acid. However, let's imagine that the other side of this chain has some branching. Obviously you've got 3 carbons to play with here, so you could make it branched. So here I hope you can see how this is also another option for an isomer of this ester. So there we have it. We've got our 2 different isomers with the same molecular formula that are still esters, and I hope that it makes sense how I drew those. If you felt a little unsure on any of the stuff in this video, just make sure that you pause it and you make some notes on all of the individual bits you got stuck on, and you'll be getting it right in no time.
Ouch! This is why in some videos I explain scratches.